Alrighty, welcome back to 353. So where we left off before taking the brief detour for the threads lab is we implemented a lock, and our lock sucked. So had that busy wait problem where it was just an infinite loop reading a value over and over again. One, it didn't work. It let two threads actually acquire the lock at the same time. Also had a busy wait problem where even if another thread has the lock and it knows it can't acquire it, keeps on trying and trying again. And also, it was not fair. We get to solve all of those problems today. So, you can implement locks in software with like minimal hardware requirements. So like the lowest hardware requirements is that memory loads and stores are atomic. Again, remember, atomic means it either all happens or it doesn't. There's no in between. And the other requirement is that instructions execute in order. And with just those two hardware requirements, there's two main algorithms. There's like Peterson's algorithm and Lamport's bakery algorithm, which is essentially like processes essentially take a number and then try and like order themselves in order to get the lock in the same order. However, they're slow, they don't scale that well, so as more processes are waiting for the lock, it gets slower and slower and slower, and processors actually also execute out of order because, well, turns out that is a faster thing to do, and that's all covered in your hardware course, or at least some of it. So we're going to assume the real-life situation where we have hardware support for atomacy. So we will assume a magical atomic function, and this is what we will use to implement our mutex. So the generic name is called compare and swap, and if it was represented as a C function, it would look like this. So it takes a pointer to an integer, and that is the memory location that I am trying to modify. So I'm trying to change a value here or read a value here. And then it takes two other arguments, an old value and then a new value. And what it returns is it returns the original value at that memory address. And what it will also do is it will swap that value at that memory address if it is equal to old. So if the original value is old, then it changes to new. So if we do compare and swap, we give it, say, a pointer to an integer. Remember, we just had a lock that is represented by an integer. So if we give it the pointer to our lock value, and we say the old value is 0, and then the old value is 1, atomically what that will do is if the current value is 0, well, it will read a 0, and 0 is equal to old, so 0 is equal to 0. So it would atomically change that 0 to a 1. And we don't have to worry about concurrency or anything like that because compare and swap is an atomic function itself. So it will change the value of 0 to a 1 atomically, or in this case, since that value goes between 0 and 1, in the case that the original value was 1, well, compare and swap would just return 1. So it would read the original value. So if the original value is 1, well, it's not equal to old, so it won't modify anything, and it'll just return 1. So now if we implement our lock like this, our lock can just look like compare and swap, just in an infinite loop. So if the current value of the lock is 0, then it would change from a 0 to a 1 to indicate that this thread has the lock, and then it would break out of the while loop and return from the lock call. Otherwise, if another thread tries to acquire it and another thread has set it equal to 1, well, compare and swap returns 1, and it's just while 1, and it'll infinite loop over and over again. So, So any questions about that? So this doesn't have the problem where two threads can call lock and two threads make it past lock because this compare and swap is atomic. So if the current value is 0, whatever thread happens to call compare and swap first, we'll change it to 0 to a 1, break out of the while loop, past lock, and then the other one could not do it. And yeah, so there's another question. How does this improve performance compared to the infinite loop in the last lecture? This still has a busy wait, but this implementation actually works as a lock and actually ensures mutual exclusion. So still has the problem with busy waiting and not being fair. Yeah.
How do we make sure that compare and swap is atomic?
So the question is, how do we make sure that compare and swap is atomic? So compare and swap is like a literal CPU instruction that is atomic. So it's like hardware implementation, you don't have to worry about it. Someone else did the hard work for you. And pretty much every single processor everyone has will have an instruction like this or instruction named similarly. So it might be called compare and swap, it might be called something else that we'll see in a sec. But any questions about this? So this works. It has a busy wait, it's not fair, but it at least ensures mutual exclusion, which means if two threads call this, call lock, only one is going to make it through at a time. And the only way that the other one passes is that while the other thread just unlocks it, sets it equal to 0, and then the other thread can go ahead and swap it from a 0 to a 1 to indicate now it has the lock. All good? All right, so this is our first crack at a mutex. It's not exactly a mutex because, well, busy wait and not fair, but, and so, yeah, in this, so there's a question, how's the logic work again? So if currently, like the value at L is equal to 0, what happens to compare and swap? So compare and swap, it will read the value, so it will read a 0, and then compare and swap returns 0. But we know because we set old to 0 and new to 1, that if we get a 0 back of like that was the original value, we know that this has actually changed the value of 0 to a 1. So in the case that we change a 0 to a 1, compare and swap returns 0, and while 0 means we break out of the while loop. Okay, so that implementation is something called a spin lock. So compare and swap is like the actual hardware atomic instruction. On x86 might have a different name. They call it comp exchange. Why? Because they like making things shorter. Short for compare and exchange. Compare and swap, compare and exchange mean the same thing. They pretty much solve the exact same issue. They just named it something, and you know, hardware people like making things shorter, so it has a very dumb name. So we need to solve some other problems. Sometimes like having a spin lock is okay if our critical section is quite small. Maybe just waiting, if like trying it a few times isn't that big of a deal. But it's more of a big deal if we have like a uniprocessor system, so something with a single core on it, because we know if we can't get the lock, we should just yield to a different thread and let the kernel schedule another thread or another process, and then maybe that frees the lock. On a multiprocessor machine, yeah, spin locks may be good if our critical section is really, really small, because to yield, you have to do a system call and all of that, and then the schedule has to run, so maybe it's better to just try again sometimes. So we're going to solve some issues. First issue we are going to solve is that busy wait problem. So to solve busy wait, we can simply add a yield. Oh, yeah?
Why is it called a spin lock?
So the reason why it's called a spin lock is it's named after this while loop. So the while loop constantly tries again and again and again. So kind of like spinning your tires aimlessly, spinning something. Basically that it's called a spin lock because this is an infinite loop. While it's an infinite loop while some other thread has it locked. Okay, so in order to solve that busy wait problem, maybe we do something like this, where if we get a 1 back from compare and swap, which means another thread has the lock, well, oops, we write a body in the while loop and just yield. So we just say, go ahead, scheduler, please just schedule something else to run. But now we have a new problem. So consider we have like 8 threads, 1 got the lock and then 7 did not. Well, if we also want to be fair, all 7 threads would yield. And then as soon as we unlock it, well, we know that only 1 of those 7 threads is going to be able to successfully get the lock, but all 7 of them are going to try again when we know that 6 of them are kind of doing it in vain. So we also have no control over which of those threads is going to get the lock first. So say thread 2 is the first one to try and then yielded itself. Well, we would like to be fair, and if thread 2 is the first one that tried, it should be the first one that gets it when it gets unlocked. So we need to be able to reason about that too and be fair, and easiest thing to do is just to have a queue of threads, first in, first out, pretty much the fair thing to do. So just a yield, not good enough. So we can go ahead and add a wait queue to the lock. So we'll just add a queue of threads, and each time we don't get the lock, we'll just go ahead and add this current thread to the wait queue and sleep. And then now in the unlock, we add a bit more code here. So if you are unlocking, so you are done with the lock, you might just check the threads that are currently in the wait queue and then just wake up one thread. So if there's 7 threads sitting there, you only wake up one, and this assumes that we have a thread sleep, so it puts the thread to sleep. It essentially blocks the thread until another thread wakes it up. So this thread would essentially unblock just a single thread in that wait queue. So turns out there is 2 problems with that, with this code as written. One is called a lost wake up, which means there may be a situation, and then this fun concurrency stuff is what you will have to do on exams, and when you are programming, you have to reason about these things. So turns out that through different threads executing this concurrently, we might have a situation where a lost wake up occurs, and it's going to be our job to illustrate that this is possible. And a lost wake up just means a thread will go to sleep and then never wake up. So it'll essentially go into a coma, I guess. It'll be blocked forever. It should be the case where it puts itself to the wait queue, goes to sleep, but it never wakes up. And all we have to do is demonstrate a situation where that might happen using 1 or more threads. And then there's a second issue where the wrong thread would get the lock. So even though you are first in the wait queue, there is a situation that another thread is going to acquire the lock instead of you. So we're going to have to reason about these. So first is the lost wake up example. So looking at this code, we're going to have to come up with a situation ourselves where, in this case, we only need 2 threads, where 2 threads are running, and there's a situation where one of them gets put to sleep forever. So as a hint, here, I will switch this. So you can consider we have 2 threads and assume that, let's say, initially thread 1 so thread 1 has the lock, and then the current value of the lock in memory is equal to, 1. So is there a sequence where these 2 threads can run? And I'll give you a hint what function they are running, where thread 1 is running unlock, thread 2 is running lock. So is there a situation, and in this case, we just, for the sake of argument, we just argue concurrency. So assume we just have like a single processor running, and then we just concurrently switch back and forth between the threads. Is there any order of switching between these threads where thread 2 puts itself to sleep and then never wakes up? So I'll give you a second to look at the code and think about that a little bit. And yeah, we have 1 potential answer. I'll wait a little bit more. All right, we're good? Someone want to take a stab at? Yeah?
The unlock and then the next thing process occurs between thread 1 or whichever one recognizes the lock, but then before it adds itself to the wait queue.
So for this, we have to just pick a thread to run first, and then like thread 1 is running unlock and thread 2 is running lock. So which one runs first? Yeah, anyone? Which one? Unlock first. So thread 2 would run first. So if thread 2 runs first, then what would happen is we change the value of the lock from a 1 to a 0. And then, well, if we switch over to another thread, so it doesn't really matter if we go ahead, we execute this line, and then we switch to thread 2. Thread 2 is calling lock, so it will do compare and swap first, and then see, hey, the current value of L is 0, so it would change that, atomically it would change that 0 to a 1, and compare and swap would return 0, so we wouldn't, so while 0, that's false, so it would block here, it would go here, and then it would be done the lock call. So that's fine. So that works as expected. Thread 1 just gave up the lock that it had, and then thread 2 acquired the lock after it gave it up. Totally fine. Yeah.
Thread 2 locks.
Yeah, so let's go back. So original situation was the value of the lock was 1. Thread 1 has the lock. It's calling unlock. Thread 2 is calling lock. So this time, let's assume that thread 2 runs first. So it's calling lock. First thing it's going to do is compare and swap. Current value is 0 or 1. So it's going to return 1, and it's not going to swap because the current value is not 0. So compare and swap returns 1. So now the next instruction it would execute is right here. So do we keep executing thread 2 or do we switch to thread 1? Yeah.
We switch to thread 1 to run all the unlock.
Yeah, so we switch to thread 2, or sorry, switch to thread 1, and it starts running the unlock code. So this is thread 1. So it would change the value of the lock from a 1 to a 0, and then it might check, hey, are there any threads in the wait queue? So if I put like the wait queue up here, whoops. Currently it's empty, so I'll just use Python syntax. So it's currently empty. So is there any threads in the wait queue? No. So it would go ahead and skip this and then make it to the end, and it is now done unlock. So end. Okay, well now we have no choice. We can have to switch back to thread 2. So thread 2 is going to do this. It's going to add itself to the wait queue. So now our wait queue is going to have thread 2 in it. And then it puts itself to sleep. So now thread 2 is slept. It's blocked. It's never waking. So thread 1 should have been the one responsible for waking it up, but it wasn't. Thread 1's already done. So that makes sense why that works. So thread 2 is now gone forever. Well, it's blocked forever. So questions about that? Okay. Clear? Good? So with most of these, again, just assume that we have some threads. They're doing some function calls. It'll be a bit of practice to like figure out what situations are probably bad. So for some more practice, let us see if we can do the other situation where the wrong thread gets the lock. So as a bit of a hint, I'll say that thread 1 has the lock again, and then we have some other threads. So we have thread 2, and we have thread 3. And currently, we will assume that we're in the situation where in our wait queue, whoops, we have thread 2. So thread 2 is sitting right here, wants to be woken up from the sleep. It is in the wait queue, so it should be the next thread that acquires the lock as soon as thread 1 unlocks it. So thread 2 is in the sleep. Thread 1 is starting the unlock call. Oops. And then thread 3 is starting the lock call. So, is there a sequence of executing thread 1 and thread 3 and thread 2, I guess, but it's currently blocked, such that as soon as thread 1 unlocks the lock, well, it should be thread 2 because it is the next in queue, but is there a situation where thread 3 can come in and swoop it? Yeah.
Thread 1 unlocks the lock, but then it does not progress into the threads into wait queue if statement, and then thread 3 just runs into while concurrent swap, and then it grabs the lock.
Okay, you're going to say the same thing? Essentially the same thing. So, situation we could have in this case is thread 1 executes the line where we change the value of the lock to be a 0. So it changes it from a 1 to a 0. So it executes this line. Right after it executes this line, we immediately switch to thread 3. If we immediately switch to thread 3 is going to do the compare and swap. So it would currently atomically, this has all happened atomically, so we can't switch in between doing this. It will read the value at that memory location, currently 0. Okay, well, because it read 0, and then because in the arguments old value is 0, it's going to swap that 0 to a 1, all atomically. So it's going to change that 0 to a 1. And then compare and swap will return a 0, which means we finish, and then thread 3 is done the lock call. And now it has the lock. So thread 3 just kind of swooped in. So what would happen if we did this to completion? Well, thread 1 would execute. It would check if there are threads in the wait queue. Okay, well there is. Maybe it just removes it from the wait queue after it wakes it up. So now it's woken up. Thread 2 can now run. So let's say thread 1 just finishes. So thread 1 is done unlock. And now thread 2 wakes back up. So thread 2 would go and do the compare and swap again. And then it checks, oh, the current value is 1. Some other thread has the lock. So it would go ahead and add itself back on the wait queue and then put itself to sleep again because some jerk, aka thread 3, came and just kind of swooped the lock. It stole it from out under it. So that makes sense? So now we get to solve this issue. So just so you have it here, so oops, that's not it. So here's the lost wake up example. So here's the order of threads. So here I ordered them differently. So thread 1, thread 2 holds the lock. The example I did had thread 1. Here, just so you have it, just shows the lost wake up example where thread 1, in this case, never gets woken up. And then similarly for the wrong thread getting the lock, here's the sequence of calls here at the bottom, just so we can go ahead and argue about it. So, to fix this, it looks a bit ugly. Looks like that. Oh, yeah, it looks like that. Yikes. So, there is a fair amount of things going on here. Does that look fairly readable to everyone? Everyone looking at it? All right, so let's make it a bit more readable. So this is essentially just integrating that wait queue into the lock. So we're just defining a struct. So the struct, this int lock, That is the L I was using before, so that is the integer that's supposed to represent the state of the lock. 0 means unlocked, 1 means locked. And then I'm just making that queue explicit. So this is just the wait queue. So these are all the threads that are currently waiting for the lock. And then I now have another int guard. So this int guard is going to be a spin lock. So I'm going to use this as a spin lock, but the rule is that I'm going to use guard as a spin lock only for my lock and unlock functions. So no thread will have guard after the lock or the unlock function. The rule is I will only use the guard while I am executing these functions. So, looks a bit ugly, but essentially, assuming that guard is just a spin lock, which it is, this while loop, well, that before is essentially just a lock of guard, right? That was what I had way before originally. So this was my proper implementation of a spin lock where it worked. It had some issues, but turned out it actually worked fairly well. So I'm just using that, and I'm only using it internally here. So I'm only going to use this guard to implement my lock and unlock. So this whole thing here, this whole while loop here is essentially a lock of the guard. This setting the guard to 0 is basically an unlock of the guard, as with this. So it might make it a bit easier to read if we do this. And here, why there's an unlock. So if I call this lock function, so this is supposed to be like the mutex lock, then the rule is I lock my guard so only one thread can execute this at a time, because remember what data races are. I don't want concurrent accesses to the same memory location. In this case, the queue, and also adding itself to the queue. So I lock the guard, and then I check if currently we have the lock or not. So I don't need compare and swap for that lock variable because, well, I have locked the spin lock, so I'm the only thread that actually can be executing this at a time, so we don't have to worry about concurrency within the lock function now. And then I'll check the current value, so if it's 0, it means it's unlocked, means I don't have to wake anything up. All I can do is just change that value from a 0 to a 1, says now that means I have the mutex, and then I'm just sure to unlock it before I'm done this function. And then that's all I have to do in the case that no other thread was waiting. If another thread was waiting, well, this basically just adds myself to the queue. So this would throw it to the back of the queue. And then I unlock the guard because, well, if I still have it, then no other thread can try calling lock. No other thread, turns out, can call unlock. So I might have to make sure I unlock it before I go to sleep. And then when I wake up, it would just continue back here. And when it continues back here, the way we're doing this is because now that it is protected, well, let's look at the unlock call. So same thing, this while compare and swap, that is the same as just locking the guard. Then it checks if the queue is empty. So if the queue is empty, all it does is it knows that the current value of the lock is 1. So it just changes it to 0, and then it's done, and then it can just unlock the guard before the whole function. Otherwise, if there is another thread in the queue, well, the current value of the lock is 1, and I don't have to change it from a 1 to a 0 and then try and have the other one change it back from a 0 to a 1. So I'm just going to transfer the mutex. So I'll keep the value of the mutex as 1, but I'll just wake up the next thread. So only one thread will wake up, and then the current value of the lock will still be 1, but the way that it kind of works internally is that we're transferring the lock to the other function. So it's still a 1, but it passes the lock call, and it should be the case where, well, now I'm done with unlock, so I don't have the lock anymore. The other thread has the lock. So, questions about this? So, a bit ugly, but if you kind of just get rid of the big compare and swap everything and change them in and realize that guard is a spin lock, then kind of makes sense. Is there any issues with this? Yeah. Yeah, so this actually still has a very, very slight issue. So say you get put to, or say you are trying to acquire the lock. Say we have two threads. So this is a much, much, much subtler bug. So you have two threads, and currently lock is equal to 1 because, I don't know, thread 2 has the lock. So what could happen is if thread 1 calls lock, then it could acquire the guard, no problem. Then check the current value of the lock. Okay, it's 1, so it goes here. So it would add itself to the queue. So let's say we have our queue here. So let's say it adds itself. So thread 1 gets added to the queue. Then it unlocks the guard, and then it can context switch right before it goes to sleep. And then, okay, well, let's say thread 2 calls unlock now. So it would go ahead, it'd be able to grab the guard lock. Then it would check the queue. The queue is not empty, but it would go here, and then it would try and wake up a thread. So it would try and wake up thread 1, but thread 1 is not asleep. Shit. So turns out that this is a very slight problem, but it's actually one we can detect. So we know that essentially the thread 1 is about to go to sleep, even though we're not sure it might not. So thread wake up might just give us an error, say, hey, that thread's not asleep yet. But because we actually know for a fact that it is about to go to sleep, we might just retry this and retry waking up the thread until it's actually successful. And then finally, we don't have any more issues. But even this gets like 95% of the way there. But with threading libraries, if it's not 100%, well, then it's still broken. Yeah?
But what if you already have something in the queue?
Yep.
Sorry, you already have some thread that's in the queue and asleep. Then when you call the thread wake up, it's like you have something to wake up. So you can't detect the error.
So if there's some other thread ahead of it that we need to wake up, that means it was in line first and it should get woken up. So that's okay, right? So yeah, if there's another thread, it's okay. It's like a very subtle thing is if I'm about to go to sleep and it's also trying to wake me up, that there might be a case where I'm not asleep yet. So try as we must, we still had a bit of a data race, but I could have fixed it on the slide, but the slide already scared you as soon as I showed it anyways, so. It got most of the way there. So any questions about this? Is this slide less scary now that we went through it? All right, good. So this minus that little fix, this is the implementation of a mutex. So you can just use it, but under the hood, this is essentially what the implementation looks like. So we still had, So we still had a bit of a data race in the case that a thread called lock, it got interrupted before it actually went to sleep. But because it was safely added to that queue, well, thread wake up can just try and wake it up until it's successful because we know it's about to fall asleep. So we just retry it over and over again until it finally wakes up. So with all of these, our core issue was remembering what causes a data race. So I've said it like a second time, dedicating a whole slide to it. So very, very important because this is all concurrency things. So in this case, a data race, we have two concurrent actions to the same memory location, and at least one of them is a write. So knowing that, there might be cases where for performance reasons, you might be like, oh, okay, well, that means if a bunch of threads are only reading the same memory location, there's no issues. So what about if in my application, I like rarely write to a memory location, and most of the time all my threads are reading to it. If I just used a plain old mutex, that means only one thread can read it at a time, and I might have bad performance because, well, only one thread can run at a time, nothing can run in parallel, and it's slow. So if I want, I can have as many readers as I want. Don't need a mutex as long as nothing writes to it at the same time. As soon as we have a write, then we have to make sure only one thread is executing at a time. So there is a special kind of lock that has different lock modes depending on whether you are reading or writing a memory location. And they have a very, very, very creative name. They're called read-write locks. So with mutexes or spin locks, you have to lock the data even for a read because, well, you don't know if a write can happen in another thread. But really, like I said before, reads can happen in parallel as long as there's no write. So the rule is there is something called a read-write lock, and there are different lock calls depending on whether you are reading or writing. And the rules are multiple threads can hold a read lock simultaneously. So it's called a read-write lock. So there is a lock specifically for reading. And if you lie to the compiler and you're actually, or not the compiler, but like lie to your program and you lock it for reading and you're actually writing, well then you have a data race and your program's going to be wrong. So the other mode that we can do is we can do a write lock, and that makes sure only one thread has this lock. So if there are currently other threads reading, it will wait for them all to finish reading so that it can have exclusive access to this lock, and essentially the write lock just treats it as a mutex. So we can implement that just using mutexes if we want. So if we really wanted to, this would be the implementation of a read-write lock. So same idea as before. Well, we have this lock that actually just represents mutual exclusion. So for our read-write lock, it's just we just lock that lock and unlock that lock because it's supposed to ensure that only one thread is doing this at a time. Locks have mutual exclusion. So we're just going to just write lock essentially just delegates to it and says just lock that lock, and then write unlock says just unlock that lock. And then to implement the read lock, well, we're going to have, it's going to access that lock too, and it will go ahead and try and lock it, or if it is already acquired, it will just keep track of the number of readers. So it keeps track of the number of threads that have the lock essentially acquired for reading. So we have an int called number of readers, and we create a guard so that we don't have any data races with this variable. If we had a data race with that, we might not know how many readers currently have the lock. So in the read lock, our implementation is we lock the guard, and then we increment the number of writers. So we're keeping track of, the number of readers. So we're keeping track of the number of readers. So initially, the number of readers would be 0. If we increment it, and then we changed it from a 0 to a 1, which indicates that I am the first reader, well, that means we don't have the lock or anything. So if I'm the first reader, I have to acquire the lock. So then I have that lock that is meant for mutual exclusion, and then I can unlock the guard. So now if another thread was to call read lock, well, it would get the guard, increment the number of readers from like 1 to 2, and then check. Well, it's not the first reader, so it knows that another thread already has the lock for reading, so it doesn't need to acquire this lock because it's mutual exclusion. So it can just unlock the guard, and then we can have as many readers as we want. 2 to 3, 3 to 4, 4 to 5, all good. And then for the read unlock, well, we have to acquire the guard because we're going to change this n readers. So if 2 threads have the lock open, well, then we would decrement the number of readers from 2 to 1, and then we would check, okay, well, there's another thread that has the lock, so we wouldn't unlock it, and we can just go ahead, unlock the guard. And then if we were the last thread, so we changed the number of readers from a 1 to a 0, we know that we're the last reader, so we should just unlock that mutex. Yeah?
Wouldn't this start the write operation? Like, if you had a continuous stream of reads and you never ended up with the number of readers equals 0, then you would never end up writing.
Yeah. Yeah, so that's a good point. The question is, wouldn't this starve or can lead to starvation the read thread or write thread if we have a lot of readers and they just keep on reading and reading and reading? And the answer to that is yes, in this implementation. The real one would not have that, so it would just cut it off. If like the read thread or write thread tried to acquire the lock, it just wouldn't allow any new readers until the write thread gets it. So it would be fair. This implementation works, but it's not fair. Yeah.
So like, what this is doing is it's just saying like, if you have a read lock, it means like nothing else can write to it, basically?
Yeah.
Okay.
Yeah, so this is just preventing that data race. So data race, 2 concurrent accesses, at least 1 is a write. So that's still true for this, but it lets as many readers as possible.
Okay.
But in this case, before, like, you just have 1 thread doing it at a time, but now I can have either like 8 threads all reading at a time or a single thread writing. I can't have both. All right, any other questions about this one? So this, again, whether or not you want to use this instead of a mutex, pretty much is performance reasons. For this course, we won't ever actually use a read-write lock, but good to know because many of you will be writing programs. I assume you want to go fast. So if you go ahead and look at it and you know reads happen more than writes and you add threads to it and it's slower, well then guess what? You probably need to do a read-write lock or it's just not worth it to use threads. Yep.
So the lock that we see here, for example, in a write lock, is that the mutex that we talked about earlier? Because the guard lock we said was a spin lock.
Yeah, so in this case, the lock is like just a mutex, and this guard could be a spin lock or it could be a real mutex if we wanted to. So doesn't really matter. It would depend mostly whether or not guard is a spin lock or a mutex. Just depends on performance reasons. All right, any other questions with this? So we actually kind of know how mutexes are implemented now. Joy. All right, so the whole reason to do this is just to know how they're implemented and make sure that they're implemented correctly. And well, guess what? To implement them, we also have to argue about concurrency, just like you will have to argue about concurrency for your programs. So if you want to prevent data races, we need critical sections. So mutexes or spin locks are the most straightforward locks. In order to implement them, likely everything just needs hardware support for that. That compare and swap instruction, basically every single CPU on the planet has that now. And well, we need some kernel support for like waking up threads and putting them to sleep. Spoiler alert, the sleep and the wake up, that was also part of the thread labs, the 80-hour thread labs. So I took out that part, so you're welcome. So before, you had to implement sleep and wake up on top of everything else, and then how they interact has little subtle things, but we won't worry about that for now. Kernel just has to go ahead and implement them. So Also, for performance reasons, because we know what a data race is now, we can have a lot of readers, and if you want a lot of readers to all execute in parallel, then you should use a read-write lock. So with that, just remember, pulling for you, all in this together.